All right, so what we're going to work on today for the rest of the session, and again, everyone should hopefully work on this and complete it on their own if they don't finish, is we're going to actually use the Arduino to generate a time varying signal. And we're going to build a very simple amplifying circuit, and we're going to look at that with an oscilloscope. So you're going to need an oscilloscope. You're going to need an Arduino. You're going to need a breadboard. You're going to need some resistors, and you're going to need an AD820 op amp. So first thing that you want to do is you just want to get up your oscilloscope. You want to power it up. Usually these things have a startup time, and you want to connect your a probe to a channel. So you're going to need a jumper that you connect to the Arduino ground, because again, remember, we need to connect the ground clip to the Arduino. Then we're going to write this really simple program where we set a pulse width modulation duty cycle or rate, and we're going to pick this pin, and then we're going to upload this. So if we do that, what we should see is basically a 1 kilohertz square wave. And then once you get that displayed on the scope, we're going to play with this one variable. We're going to change basically the width of that positive pulse. So if you recall, when we talked about PWM, we talked about the duty cycle would change, but the actual total period is not going to change. So basically play with it, make it bigger, make it smaller, upload the code, look how the signal actually changes on the Arduino or on the oscilloscope. One thing you'll note is even though you put this long delay in here, that's not going to affect the actual signal coming out of the PWM pin, because the PWM mode outputs a signal at a specific frequency that's fixed, which should be about 1 kilohertz. And all that this analog write does is change how wide the positive part is. And that's going to get changed whenever you call this particular function, but that pulse is going to repeat automatically until you turn it off. So after we play with that, we want to build this integrated circuit right here. So we're going to you want to breadboard this. I've got 2 resistances of 1K here. The actual value doesn't really matter. We're just looking for 2 resistances that are equal. I'm going to hook my input or my PWM pin to the input here. I want to give this op amp 0 volts on the negative supply and something like positive 12 volts. This actual value is not super critical, but I want at least 10 volts here, because if I do the calculation from the lecture, you can see this is a non-inverting op amp. And if I look at what the gain would be, well, the equation for this gain is 1 plus the feedback resistance over the input resistance. Well, since I have the same resistance value for the feedback and the input resistance, I would expect this to be 1. So my total gain should be 2. So my original signal output should be about 5 volts. So the output of this, after I send it through the amplifier, should be 10 volts total. So basically, that's what you're going to want to do. You can also then, after you have this built, you want to hook up the oscilloscope to the output here so that you can monitor that. If you have a multi-channel oscilloscope, it's good to basically hook up to the input and the output so that you can see how those change. So that's what we want to do today. And I'll just quickly, I have that actually all set up here. So I will just show you what that all looks like. Okay, so you can see here. Let me get my oscilloscope probes out of the way. Okay, so you can't see it on screen, but I have a power supply hooked up so that the positive output is hooked up to this top rail here. And I have my negative output hooked up to here. I have about 12 volts difference here. Also, you can see that I have my ground connected to my ground of my Arduino, right? Because I want everything to be on the same 0. And I also have my grounding pins or my grounding clips of my oscilloscope probe hooked up to my same 0. So you can see I have my 2 resistances here, my two resistors here. This is my feedback resistor. So it's going from the output pin up here around to the input pin, right? So you need to look at the actual, pull up the data sheet so you know which pin is which. I've got my negative supply pin connected to ground through this yellow jumper. I have my positive supply pin connected to plus 12 volts through this blue jumper. This is my input resistor, which goes to ground and the negative input like it did on the circuit there. And then you can see this green jumper coming over from the Arduino. That's connected to pin 4, which is the PWM pin. So if you were to look at the output of, or you were to look at the scope, so this jumper right here is just to give me something to clip onto. So if I clip my probe onto that, and I have my grounding clip for this probe hooked onto this yellow jumper, which goes into another pin of the Arduino. And if I switch to a camera, or if I turn my camera so you can see the, yeah, let me switch the camera. Okay, so you can see the output on the scope right here. So right now I have this set to 127, which is why, if you remember, the values for that duty cycle can be 0 to 255. So 127 is right in the middle. So I basically have an even input and output. And if I was to go to my Arduino and I was to change that to, for example, 12 and upload the code, you'll see quickly. So now my pulses are very, very short, but the spacing is the same. And if I zoom out on this, you'll see I don't have a big 5-second gap because, again, the PWM pin is going to automatically repeat as that goes along. And if I now change that to something pretty big, let's go to like 250, and I upload that. So you can see these pulses are almost all on, and then they're briefly off because I almost have the PWM at the maximum value. So if I change that to something that it's a little bit easier to see, there we go. So one other thing you can see, I'm not sure if you can read this out on the camera, but I have a frequency output here. So that's 975 Hertz. So it's about 1 kilohertz. My scale on my y-axis is 2 volts. So you can see it's 1, 2.5, so 5 volts. So you can see that's the output. Now I already have, now if I hook on to the output of my amplifying circuit, and I turn on the second channel, which is channel 2 here, you can see I have matched up in time the outputs of the amplifying circuit, which are twice as big. And one thing I can do is if I vary the output of, basically if I start at right around 10 volts and I increase that all the way up to 15, this is the power being supplied to the amplifying circuit. This output value doesn't change because that output value is being determined by the amplifying value and it's not being limited by the range. But as soon as I start to decrease the power supply to the op amp below 10, now I start to get the output value decreasing, matching whatever that maximum value is being output on the power supply. So that's what you guys want to try and get working today.